My name is Hannan Dempsey, and I'll be presenting on my research creation of a 3D printed phantom for the dosimetric verification of radiation therapy treatments for pediatric brain tumours. I'd like to thank my supervisor, Pejman, for all the help he has given me in completing this project. Firstly, pediatric brain tumours are the second most commonly occurring tumour in pediatric patients following leukemia. According to the Australian Health and Welfare, 2 cases per 100,000 Australian people under 19 years old develop brain tumours. In the subcategory of pediatric brain tumours, pilocytic astrocytoma, a World Health Organization grade 1 low-grade glioma, is the most commonly occurring, followed by medulloblastoma, which is a WHO grade 4 embryonal tumour, and glioblastoma multiforme, which is a WHO grade 4 high-grade glioma, and then there are a multitude of other brain tumours that could also occur. Brain tumours are typically treated by surgery, which is the gold standard of treatment. As much of the tumour is removed as possible, but sometimes that is not possible due to where the tumour is located. If it's not possible, chemotherapy is typically given, especially to younger children, to delay radiation therapy until they are older. This is because of the detrimental effects that radiation therapy can have on a growing brain. However, in the case of particularly aggressive tumours and older patients who may be in their late teens, radiation therapy may be given. Ideally, this would be stereotactic radiosurgery, but protocols have not been developed for this to be possible at Sir Charles Gairdner Hospital. So the brain and its components. The brain can be thought of as the control center of a human. It controls all of our thoughts, feelings, and actions, and it can be divided into 3 main parts: the cerebrum, the cerebellum, and the brainstem. So the cerebrum controls.
What's her name?
The cerebrum can be divided into 2 hemispheres, the left and right hemisphere. The left hemisphere controlling speech and abstract thinking, and the right hemisphere controlling spatial thinking. The cerebral cortex is the surface of the cerebrum, and it contains 16 billion grey-coloured neurons, which is why it is called the grey matter. The axons, which are covered white, connect different parts of the brain together and is known as the white matter. The corpus callosum connects the 2 hemispheres together and sends messages across the 2 sides. The thalamus sorts any sensory input and sends it to other parts of the cerebrum, and the hypothalamus manages nervous and endocrine system functions. Finally, the hippocampus manages and stores memories. The cerebellum is located toward the base of the skull, behind the cerebrum. It controls balance, it coordinates movements and eye movements, which help with our vision, and it coordinates motor learning. Finally, the brainstem sends messages from the brain to the rest of the body through the spinal cord. It contains the midbrain, which regulates eye movements, the pons, which regulates facial movements, hearing, and balance, and the medulla, which regulates breathing, heart rate, blood pressure, and swallowing. All the parts of the brain work together, and any damage to one part can affect how the brain functions as a whole. Therefore, it is really important to reduce any radiation-induced toxicities to the brain. Pediatric brain tumours generally have high survival rates, as the most commonly occurring tumours are low-grade tumours. So patients are expected to have long life expectancies post-treatment. Therefore, it is even more important to reduce any radiation-induced toxicities to the brain, as the effects can be significant and lifelong. Radiation-induced toxicities show a positive relationship with dose received and volume irradiated, so it is really important that we restrict the amount of healthy tissue that is irradiated during treatment. Some functions that may be affected by ionizing radiation as a result of radiation therapy include attention, working memory, processing speed, learning ability, verbal skills, mathematical ability, sleep rhythms, and spatial skills, which are all neurocognitive dysfunctions. And other toxicities may include changes to hearing, vision, mood, and behavior, as well as headaches, depression, anxiety, seizures, impaired social skills, and neuroendocrine dysfunction. There is also a high chance of secondary tumours occurring. A secondary tumour is a tumour not directly derived from the cancer with which the patient was originally diagnosed. The risk factors for developing one of these tumours is previous exposure to ionizing radiation, including and especially from radiation therapy. Another risk factor is the amount of healthy tissue irradiated during radiation therapy and the patient's age when they are treated. The graph on the right shows the relative risk of second tumour diagnosis after initial cancer diagnosis by age group. As you can see, the pediatric age group has a significantly higher risk than all of the other age groups that are older. This is because pediatric patients have the highest lifetime attributable risk. meaning that because they have so much longer to live after diagnosis, they are so much more likely to develop another tumor later in life because of their radiation therapy. They are much more likely than a 70-year-old who may not live the 15 years that is needed to develop one of these tumors. And onto phantoms. A phantom is a tool used in medical physics to simulate the interactions radiation may have with tissue. Phantoms may be anthropomorphic, like the commercially available rando phantom, and they are usually based on reference anatomy of an adult. Not every patient will match the size and geometry of a commercially available phantom, particularly pediatric patients who are expected to be smaller. This is where 3D printed phantoms come in. They allow us to customize the phantom to match the size, shape, and needs of the patient. We can create phantoms based on the patient's actual CT scans, therefore they are more expected to match the actual patient's geometry. We can also alter filaments and percentage infills, which allow us to create tissue equivalent materials, and they allow us to perform patient-specific quality assurance and patient-specific treatment verification prior to treatment delivery. Given the aforementioned risks of radiotherapy on pediatric patients, using 3D printed patient-specific phantoms to verify treatment can really improve the safety of the treatments and the outcomes they experience. 3D printed phantoms were what I investigated in my literature review. So the criteria I assessed my studies on were whether they were phantom or patient-based, so whether they used the CT scans of a phantom or a patient, what dosimeters were added to the phantom, what filament was used to print the phantom, other materials used, whether they investigated varying tissues like separating the skull and the brain, whether the phantom was sliced, and whether the phantom was based on a pediatric CT scan. Some key findings from the literature included ABS filament being very unreliable and warps while printing, and PLA was found by other studies to be much more reliable, so therefore it was used in this project. The method followed by Kadoya and others to 3D print molds and fill them with plaster of Paris inspired a skull design that will be discussed later in this presentation. And pediatric phantoms, so 2 studies investigated patient-specific pediatric phantoms and also phantoms for amputees because they have geometry that differs from the reference geometry, and they were compared to commercially available phantoms such as the rando phantom. Both studies found that the patient-specific phantoms performed better and improved patient safety. Finally, none of the studies I analysed were successful in replicating skull bone with 3D printing or other techniques. So onto my research aims. There are 5 categories of thesis that you can write: experimental, theoretical, modelling, design, and literature review. My thesis is based on design. My aims included designing and creating a 3D printed, adjustable, and anatomically correct brain and skull phantom based on the anatomy of a pediatric patient, and completing and evaluating different phantom designs and creating a framework for producing cheap, accurate, and easily replicable pediatric phantoms. Future research will involve the phantom playing a role in the development of stereotactic radiosurgery protocols at Sir Charles Gairdner Hospital. So the first thing I had to do was to choose a patient. So the graphs in the top left are based on statistics from the Australian National Cancer Control Indicators. These are the statistics on which I based my decision to create a 10-year-old male phantom, as brain cancer incidences are slightly higher for males, and 10 years old is basically the midpoint of this category. I got phantoms provided by the National Cancer Institute Division of Cancer Epidemiology and Genetics in the United States, and these phantoms were also worked on by students at the University of Florida. NCI provides pediatric phantoms of many different ages and both sexes. They were created using an archive of over 1,000 patients to select the best reference anatomy for each age, and they feature over 100 organs per phantom. So on the right here, you have a CT scan of the phantom that was supplied. The first picture is the whole body, and then I segmented out the brain and the skull in 3D slicer. The first thing I had to do in terms of actually creating things was to make the brain, and this was done using the segmentation from 3D slicer. According to data supplied from the Department of Medical Technology and Physics at Sir Charles Gairdner Hospital, the average CT number of a 10-year-old's brain is 38 Hounsfield units. However, the CT scan from the NCI actually showed that the average Hounsfield unit of that brain was 62 Hounsfield units. However, I aimed for 38. The 3D model of the brain was imported into Fusion 360, and it was cut into slices that were 5 millimeters thick. Clips were added to each slice so that they would fit together, and a 0.5mm deep rectangle was cut into each slice to place film. Having film between each slice allows for a three-dimensional reconstruction of the dose distribution. The brain was then printed at 96.68% infill with generic PLA to create CT numbers of 38 Hounsfield units. This was done using a relationship between Hounsfield units and percentage infill of PLA that was investigated by other members of the UWA Medical Physics Research Group. On the right, we have my two finished brain designs, as well as a close-up of the brain slice and the film inserts, and the model in Fusion 360. Secondly, I created tumours and organs at risk. 3 tumours were created based on literature volumes for pilocytic astrocytoma, medulloblastoma, and ependymoma. And the tumours were printed in 2 hemispheres, with the top 0.5mm of the bottom hemisphere removed so that a piece of film could be placed in the brain's film holder and over the top of the tumour. Negatives of the sphere volume were cut into the brain, and they were placed in where they would be most likely to occur in a patient. Doing this allowed the tumours to be placed inside the brain, and then we could change out the slices containing the tumour as needed, making it very customizable. In terms of organs at risk, I printed ears, eyes, and a brainstem. So the ears were sliced down the coronal plane with a film insert and clip fitted so that it would fit together and we could take measurements from it. It was printed with Volcano PLA at 97% infill, as it has CT numbers of about 156 Hounsfield units. The eyes were sliced along the transverse plane and they were fitted with a film holder and clips. They had a slightly higher Hounsfield units than brain, so that they were printed with the same filament as brain, but at 97.6% infill. The brainstem was sliced along the sagittal plane and made to attach to the bottom of the brain and fitted with a film holder along its length and clips so that it would fit together. Because it is part of the brain, it was printed with the same PLA at the same infill as brain. So I trialed 3 skull designs to find the best one that would be the easiest to replicate. So this is skull design 1. It featured a skull printed at 110% of its original size at 15% infill. It was split into 3 parts that would be able to clip together, and the surface was lined with Aldax silicone putty. So the silicone putty comes in 2 parts, part A and part B. One is yellow and one is grey, and you mix them together in equal parts. And then after about 15 minutes, it sets and it dries into a hardened silicone rubber. Silicone, which has an atomic number of 14, undergoes similar interactions to the phosphorus in bone at CT energies, so we can expect silicone and bone to have fairly similar but not exactly the same CT numbers. Secondly, I created skull modes. This is based on a source in the literature by Kadoya. The negative of the skull thirds were cut into boxes, and then they were printed with generic PLA. The skulls were placed in the boxes in such a way that we could fill it with plaster of Paris powder and water mixed at a 1:1 ratio and left to dry. The 1:1 ratio was important because it had to be, the consistency of the mixture had to be as close to liquid as possible so that it could sink down into the intricate details of the skull. Similarly to silicone, plaster of Paris chemical composition contains calcium and sulfur, whilst bone contains calcium and phosphorus. Sulfur and phosphorus have similar atomic numbers, and calcium is present in both, so similar CT numbers should be expected between bone and plaster of Paris. Onto the third skull design. This was aimed to be a skull split into thirds printed with stone-fill concrete PLA, which is a filament that is 50% regular PLA and 50% powdered concrete. At 100% infill, it is possible to print CT numbers of over 1,000 Hounsfield units, which is based on a study investigated by Ma and others. However, upon printing with this filament, it was found to be extremely difficult to print any solid infill, especially at the high percentage infill needed to create this skull. Therefore, this design did not physically eventuate, but a theoretical discussion of it is still possible. So to compare the 3 skulls, I devised some evaluation criteria. Difficulty is based on how difficult it would be for someone who had no 3D printing experience to create the different skulls given instructions. The cost was based on the cost of any materials required and did not consider the cost of a 3D printer, as this is common to all 3 designs. The time taken is basically just the amount of time taken to print and construct all of the skulls, and the labor is the amount of people power required to construct them. Materials refers to just the different amounts of materials you have to go out and acquire to make the skulls, and the accuracy refers to the tissue equivalence of the resultant skull and also the geometrical accuracy. And these categories all have different weightings to suggest how important they are to the process. So the results for the brain and the tumours, the final design was a 96.68% infill sliced brain model with generic PLA. Each slice has been fitted with a film holder and clips. 97% infill spherical tumours were cut into hemispheres and can have a piece of film placed over them and into the brain. This allows for a very customizable design that can be used in many situations. The filament is easy to work with, and the 3D design of the brain and tumours should be accomplishable with instructions. Cutting the negative of the tumour into the brain may require some technical skill, but after you've done it a few times, it does become very easy. In terms of cost and materials, this requires 2 rolls of generic PLA, which are about $31 per roll, bringing the total cost of the brain to $62. Time and labour, the print time for the brain is approximately 7 days, and labour is required for designing and starting the prints. And finally, the brain achieved a tissue equivalence with a minimum CT number of 29 Hounsfield units and a maximum of 106 Hounsfield units and a mean of 80.7. This is quite far away from 38, which is what we were aiming for. So in the future, a lower percentage infill should probably be used to create the brain. It was also not uniform, which is what we expected. The printing is it can be very inconsistent just due to conditions in the 3D printer. Therefore, we expected some inconsistency, but probably not this much. In terms of geometrical accuracy, there was a 6.47% difference in height, negative 2.5% difference in width, and negative 4.82% difference in depth. The increase in height is probably down to the film holders and the clips increasing the height of the brain, and the shrinkage in width and depth is probably just due to the filament shrinking while printing. Tumours were as expected in both categories. So for skull design 1, which was 15% infill skull lined with silicone putty, it was fairly easy to work with in terms of printing with the filament and lining it with the putty, and no advanced knowledge of 3D printing is required. In terms of costs and materials, only 1 roll of PLA is required, and 500 grams of silicone putty is required to line the skull. It took approximately 4 days for the printing and construction of the skull, and labour is required with the design and putty application, but these 2 things do not take that long. In terms of geometrical accuracy, the percentage difference in height was 0.55%, width was 4.71%, and depth was 0.16%. So this is a lot more accurate than expected, given it was printed at 110% size. It is also missing the jaw, but all the other features are accurate. It is missing the jaw because of how hard it was to line the jaw with silicone putty. In terms of tissue equivalence, the minimum CT number was 588 Hounsfield units, maximum was 1,060 Hounsfield units, and the mean was 846.8. It was inconsistent, probably due to not mixing perfectly even parts of each part of the silicone mold, but it was found to be very close to what we were aiming for overall. So in total, it received a mark of 75 out of 100. So for skull design 2, which was the plaster of Paris skull made from 3D printed molds, technical skill is required to design the molds, especially because it involves cutting the negative of a very complicated object into a solid box. It is also found to be very hard to remove the skull from the molds. They were printed with 10% infill with the intention of just smashing them off and it being easy to remove, but that did not happen. It was actually really difficult. Otherwise, the printing is reliable and creating and pouring the mixture is easy, especially because it is just a 1-to-1 ratio of plaster of Paris powder and water. In terms of cost and materials, 2 1-kilogram rolls of PLA are required to print the molds, and 2 500-gram bags of plaster of Paris are required. The overall time taken to create this skull was approximately 7 days, and labour is required with the design, plaster mixing, and the pouring and mold removal. In terms of accuracy, the material and geometrical accuracy, the material remained wet for days and the plaster dried very crumbly. Features snapped off, and turned out that the skull could not bear the weight of the brain. Therefore, it was not geometrically accurate at all in the end, although if the plaster hardened a bit more and dried not crumbly, it probably would have been great. Tissue equivalence. The chemical composition of plaster of Paris makes it a good substitute for bone, but more water than intended on the package instructions likely lowered the CT numbers. Overall, it received a mark of 65 out of 100. Skull design free. The final design did not physically eventuate, but it would have been a skull printed in furs of stone-filled concrete PLA. Difficulty. The design was very easy. It is just a skull split into thirds with some clips added. However, the filament was extremely difficult to work with when printing at high infill, and it was so difficult to work with that it was decided to abandon it before it actually resulted in a physical object. 3 rolls of stone-filled concrete PLA are required at $64.95 each, and a hardened nozzle is required to not damage your printer. In terms of time and labour, it would take approximately 5 days to print if everything went completely perfectly. However, the print may fail very often and need constant fixing, which increases the time a lot. In terms of accuracy, at 100% infill, the filament is extremely brittle, and intricate features such as the jaw would have snapped off pretty much immediately. However, thicker structures would have been quite accurate. In terms of tissue equivalence, at 100% infill, CT numbers between 900 Hounsfield units and 1,000 Hounsfield units can be achieved, but printing is inconsistent due to the high pressure in the nozzle. So the winner is the silicone putty skull. So on the left and right, you can see the skull prepared for CT scanning, and in the middle are the CT scans of the skull, showing the brain in the sliced model, the tumour, and also the skull. So to accompany this design, I created a framework, which is basically a series of step-by-step instructions on how to create these phantoms. And they are very in-depth and show exactly what to click and where to click at any step. And it goes into everything you need to print the models. So for future work and recommendations, this phantom will be used to compare stereotactic radiosurgery techniques, particularly linear accelerator and cyberknife. So far, CT scans have been taken, fiducial markers have been placed, and a mesh mask and headrest have been created, and treatment plans are currently underway. This is aimed to help pave the way in developing protocols for pediatric stereotactic radiosurgery at Sir Charles Gardner Hospital. For other recommendations for future work, we could create patient-specific phantoms based on patient CT scans. Phantoms of different ages and sizes, different sizes of tumours, multiple tumours, different locations of tumours, and using the phantom to investigate new treatment modalities such as proton therapy. And alongside my thesis, I drafted manuscripts on the comparison between stereotactic linear accelerator and cyberknife, a review of the literature, and also one on phantom design titled Development of a 3D printed phantom for the verification of radiation therapy treatments for pediatric brain tumours. So here are all the references I used to construct this PowerPoint, and thank you very much for listening. Are there any questions?
Thanks very much, Hannan. Brilliant. Any questions from Hannan? Yes, that was brilliant presentation. Yes, please. We have one question from Rashid.
Sure.
Thanks, Hannan. That was a very nice presentation. So with your design, your preferred design, you had the silicone one. Yes. Is there much water used in it, like in the materials?
There would be some water in the actual silicone because when it's first created, it is wet, but there was no water added at all.
Okay, I see. So how long do you think your design would last? Because over time, these things dry out and they will lose some water. So HU number will change.
Yeah. So far, the silicone putty has been on the skull for 2 months with no change. So based on that, I could expect it to last for at least 6 months, potentially longer, but that has not been investigated.
Right. And then you suggested patient-specific 3D printing.
Yes.
So how long does it take to print it?
It would take about 2 weeks, but there are methods to quicken this. So using multiple 3D printers. And then I've got a slide on how to improve the process. So using multiple 3D printers and using printers that are able to print to a high quality at a different speed would be able to quicken this process a bit, because 2 weeks is a long time.
Excellent. Thank you.
That's all good.
So Michael.
Hi, Hannan. I'm Michael from Newcastle. Thanks for
Hi.
the talk. It was very good. I have a couple of different questions.
Sure.
The first one was, how did you, in your evaluation criteria, how did you decide the weights for each of the different aspects? So they were sort of obviously out of different marks for each. How did you decide that?
So they were basically mostly just based on, I'll just use that. They were qualitative assessments. So for me, it was really important that it would be the difficulty was like difficulty and the accuracy were the most important factors, which is why they have a higher weighting, because we want it to be able to be replicated by people with no 3D printing experience, but we also want the phantom to be accurate. In terms of cost and time, that is also really important, especially given that it takes such a long time. A shorter one would be better, which is why it has a high weighting, and cost, because that is always important to consider. The amount of materials necessary and labour receive lower weightings because I deem them to be less important, basically.
Okay, thank you. Question, so I've got 2 more questions. I hope you don't mind, Pejman.
That's all good.
Okay. Okay. You spent a lot of time in the start of your talk talking about the materials and how what HU would expect for those materials. Do you actually have any information on the actual electron density of these materials, so you can verify sort of absolutely that they fit on the Charles Gardner's CT's RED curve?
They have been CT scanned, and the electron density has been that is information we have from the CT scans. And they were also CT scanned prior to me using them in most cases.
You get the HU out of the CT scan. How do you know that what electron density that is? Are you just taking off the RED curve they've got? Are you making an assumption that it sits on that curve?
Yeah, I'm basically assuming it sits on the curve.
Okay, thank you. So last question. Sorry, Machie.
Sorry, I just wanted to add that when you open it in Eclipse, it gives you the electron density.
Okay.
My last question, just quickly. So obviously you mentioned right at the end of your talk that this phantom is for single MET patient, and that for future work could be for multi-METs. Are you able to sort of inform on what percentage of these patients are single METs versus multi-METs? Do you know that information?
I don't know that information, but I could potentially find it out. Yeah.
Okay, thank you very much.
That's all good. Thank you.
That's great. Thanks very much, Michael. We have Talat.
As I'm saying, but I think the most of the question was already asked.
That's
my, but what I was thinking, have you discussed? Maybe I missed it because I was in and out. So, have you discussed about the accuracy of the printing itself? Whatever you plan to print, the dimensions and things like this, how the accuracy of this printing is.
Yeah. So.
You didn't show any stats. Have you showed any stats somewhere in the presentation?
I've written them down in the accuracy section. So on the current slide, it does show the percentage differences in the height between the original phantom and then the printed phantom, and they were both found in 3D Slicer using the same type of height, width, and depth measurements. So that is basically the measure of how accurate the prints are in terms of geometry.
Yeah, okay. So, yeah. Good.
Thank you.
Thanks very much, everyone. Thanks, Hannan.
Thank
And
you.
it's great, as Hannan mentioned, there would be 2 draft of papers out of this project, and also potential for another one when we start measuring, comparing CyberKnife and Linac, which would be hopefully the 3rd one. All the best, Hannan.
Thank you.
Well done.
Thank you very much.
I'm going to stop recording.